Hello everyone, welcome back to MGF1106. So in this video we're gonna start a new chapter, and before we start this new chapter I would like to mention one of the character in the series. I don't know if you guys watch this series. It's a TV series, a TV show, pretty long time ago. The show name of Boardwalk Empire. And in that show, there's a character, and this guy is a non-fictional character. This character is non-fictional. It means this guy is real, and his name is I remember his name is Arnold Rostan. He's a Jewish guy. In this guy is he considered as a god of gambling, and he make a lot of profit. He make a lot of money by gambling. He play poker, and he did a bet, and he even had a bet company. He make his own company. Luckily, at the end, somebody shot him because Arnold Rothstein he made business with mafia too. Because in that series, in the TV show, they talk about mafia also. However, I don't want to talk about that part, but I want to mention this name because again, this guy is considered as god of gambling, and one of the news reporter, that guy asked him how come Arnold Rothstein can make a lot of money with gambling. And this is what Arnold Rothstein said. He said that the reason he could make a lot of profit with gambling because every time he throw a bet or every time he gamble, he always makes sure that the possibility in his favor is more than, the possibility of winning in his favor is more than 70%. Okay, possibility, what I mean over here is the probability of winning. So the question is how come he can do that? Well, we don't know how, but maybe after learning this chapter, you may have the answer for yourself. How come he can use the concept of probability to make a lot of profit with gambling? Okay, so in this chapter, we'll be discussing probability, and the way we discussing probability in this chapter, we're not gonna go through all section in the same way as we used to in previous chapter. So if you look at our chapter here, chapter 11, we have so depends on some textbook, but it's the textbook I have it here. The textbook this textbook over here, they put probability. They talk about probability right away. You see that on the first section. However, I'm gonna start this chapter over here with section 11.7. Okay, and then we just jump to 11.8. Then after we know these two sections, we're gonna go back to talk about probability, which is the concept Arnold Rothstein used to make a lot of profit based on with gambling. Okay, so in this video we will be discussing concept of counting principle, fundamental counting principle, and permutation. Okay, then next video we'll be discussing a combination concept. Okay, so let's get started for our lecture today. So let me delete this name. So Adnan Rostang, okay, remember that this guy is very famous, guys, very popular, guys. At that time, he lived at the beginning of the 19th century. So I have to say that a lot of people know him. Okay, so let's start with section 11.7. Okay, so I'm not gonna put the section number. I've just put the name, the title for the concept we cover today. So we're gonna do fundamental counting principle. Okay, and on the second part we will be talking about permutation. We need to know what a counting principle is. We need to know what permutation is before we know how to use probability. Okay, how to do probability. Now, what they have a reason. Actually, they have a reason behind that why we talk about counting principle and permutation in the same section. The thing is this. These two topics here is related to each other. The permutation is actually based on the counting principle itself. And use the counting principle, we can get the formula to calculate permutation. So they are related some way, somehow. Okay, and when we talk about example, when we go through example, you will see how they are related. Okay, so let's talk about the first part. Let's talk about counting principle first. So let me go ahead and box this. Okay, our title. Okay. Okay, so on the first part, let's talk about counting principle. So what is counting principle? Of course, we look like we have to count, right? Yeah, definitely we have to count, but how are we gonna count it? So this is a definition of counting principle. Very interesting definition, and it's gonna help you understand better what counting principle is. Okay. If if we can choose one item, if we choose one item from group M, from group M, I have to say that this is not really the definition, but it looks like the method of solving problem using counting principle. Okay, but some ways it look like the definition, because the principle, I'm not going to say the principle is definition, but the principle is the method of solving problem by counting. Okay, so if we choose one item from group M, okay, and the second item, from group N, then the total number of two item choice is M times N. Okay, so this is what it means. It means that if we have a group M, okay, and this group M has distinct member, a distinct element, okay, and we have group N, and we in this group N we have distinct N element, okay, then we have M times N distinct way. I'm sorry, we have M times N distinct way to create a group with two items. Okay. Okay. Now let's jump into our first example right away. Then you will understand. Okay. Example number one. Example number one. Okay, I have something like this. Let's see where I get okay. So example number one. Okay. So I have a problem, I guess. Okay. Example number one. Oops. I don't know, for some reason the mouse it doesn't have it's run out battery, I think so. Okay. So I have a problem like this, and I'm going to use the counting principle, okay, to solve this. A restaurant offers 10 appetizer and 15 main course. You see that? It looks like a first group, there's 10 appetizer, and the second group is the course. They have 15 course. In how many way can you order 2-course meal? See that? 2-course meal. How many method? How many way you can order a 2-course meal? So how we do that? Based on the counting principle, we what if I have something like this? What if we don't have counting principle? How are we gonna do this problem? So we have if we go ahead and start counting, right? So we have the first answer. So let's see. So this is what is. I'm gonna go ahead and list all of them out so that you understand. So we have 10 appetizers. So we have the first one, then we have the second one, then we have the third one, and so on. Okay, we have 10 of them. Then we have 15. So main course. So this is appetizer. Okay, appetizer. And this is second main course, the third main course, and at the end we have 15. Well, so this is course. Okay, so think about it. If we go ahead and pick a meal, and the meal here contain 1 appetizer and 1 main course, so it means we can go. We're gonna pick this one, go with that one, right? That is one of the option. Or this one go with this one. That's the second option. Okay. So for the first appetizer, actually we can combine the first one with the one of the 15 course. So we look like we have 15 option, right? Then on the second appetizer, we will also have 15 options, and the third one we have another 15 options. So if we apply the counting method like that, if the number is pretty big, or maybe we have 3 group of elements, then it's very hard for you to know how many options we will have. So that's why the counting principle is going to help you. So in order to solve this problem, okay, using the counting principle, we have 10 appetizer option, we have 15 main course option. So total we will have 10 times 15, which is give you 152 meal course in this case. 2 course meal. I'm sorry, 2 course meal. Okay, 2 course meal, because you multiply them. We have 15 elements here in the first group. It's the first group. We have 10 elements in this first group. We have 15 elements on the second group. Then totally we have 10 times 15, which is 150 2 course meal, 150 option. Okay. Now let's do another one. Let's do another one. Example number 2. Now, what if I have something like this? Okay, let's see how we do this one. Okay, so a pizza can be ordered with two choice. Okay, so look at we have the size, group size over here, right? And group size over here we have medium, okay, and large. It look like we have only two elements here for groups, for the side group. Then for the crust group, we have thin, right? We have thin, okay. We have a thick, and we have a regular. Look like we have three elements for the second group. Okay, and for the topping, hey, when you do it, when you understand already, you don't have to list everything down like that. Okay, the way I do this because I want you to really understand what is going on over here. So we have topping group. We have total. We have five. 1, 2, 3, 4, 5. So we have 5 elements in this group right over here. So we have beef, right? We have beef. We have sauces. We have pepperoni. Okay. We have bacon, and we have mushroom. So we have 5 elements here. So we have 2 elements here. We have 3 elements here. We have 5 elements here. So total, how many one topping pizza can we order? Okay, how many one topping pizza we can order? One topping. How many one topping pizza? Okay, so let's see how we do that. So we have this, we have this, we have that. So look like the total we will have is what? Total we will have is 2 option here, multiplied by 3 option here, and we multiply by 5 option here, right? Which is give you 30 pizza. There you go. Okay, because think about it, we can pick like we can go from go with the side, medium, thin crust, and the beef. That's one of the option. Medium, thin with the sausage. The second one, medium, thin, and pepperoni. If we keep going like that, you see that if we really count it when we go and we list them out, it take us a lot of time, right? That's why the counting principle is gonna help you solve this problem easier. Okay. Okay, example number 3. Okay, how about this? Okay, no problem like that. Answer. Okay, you are taking a multiple choice test that has 6 questions. Each question have 3 answer choice. Okay, with 1 correct answer per question. 3 answer choice, there only 1 correct answer. If you select one of 3 choice, if you select one of these 3 choice for each question and leave nothing blank, in how many ways can you answer the question? Okay, so let's do a quick summary. So we have 6 questions, and we have 3 answer choices, and there's only 1 correct answer. 1 correct answer. If you select one of these 3 choices for each of the question, you will leave nothing blank. In how many ways you can answer the question? So there's 6 questions, and it's only 3 choices. So think about it. You have 6 questions. The first question you have 3 choices. The second question you have 3 choices. The third question you have 3 choices, and the 6th question also have 3 choices. Then of course, if you go ahead and apply the counting principle, you will have the total is 6 times 3, which is you have 18 ways. We have 18 ways to pick the correct answer. Well, out of those 3 choices, we don't know which one is correct answer, but there are totally 18 options you can pick. Okay, so 18 options you pick is a lot. So if you think about it, that's why I say when you have a test and the test is a multiple choice, don't ever think it is easy. Because most of the time when you do when you pick your answer randomly, it's wrong. And think about it. You have 6 options. You have only 3 choices for each question. It total give you 18 options already. 18 options. That's a lot, guys. So there's no way. It's very hard for you to get 100% on your multiple choice test. Very hard. Okay. Now, how about example number 4 right here? Let's see if we can do this. Okay. Okay. Okay, this problem is pretty interesting right over here. Okay. Electronic gate can be opened by enter 5 digits. So we have totally 5 digits. Okay. 0. We have 5 digits out of this number. Okay. Okay. 1, 2, 3, 8, 9. So totally 10 number over here. But the gate code has only 5 digits. So we pick 5 digits out of this. Okay, out of this number. In how many different keeper sequence is possible if digit 0 cannot be used as the first digit? Okay, so the way we do this problem is a little bit from what we had in the previous example, because the counting principle here, you see that is not pick an element from a group and another element from another group, but we look like we pick a whole group, okay, from this number here. So the way we approach the problem is a little bit different. Okay, so let's see how we're gonna do this. Okay, let's see how we do this. So we know that this is 5-digit number. It's a 5-digit number. So it look like that I'm gonna go ahead and draw 5 space, 5 places. Okay. Okay. So it look like that we're gonna go ahead and put the number over here, and we want to see how many options we will have out of this number. Now let's consider over here is the first position, this is the second position, this is the third position, this is the fourth, and this is the fifth position. Now you have totally 10 digits over here, but of course this digit 0 cannot be used as the first digit. So if the digit 0 is not used as the first digit, it means that we have from 1 to 9, there's only 9 options here for the first position, for the first digit position. Okay. Now for the second position, we allow to have 0. Okay. It means we have totally 10 of them. It means the number it means one of the number can be repeated. Think about it. Over here is 3. Over here it can be 3. That's fine because it never say anything about a repetition, a number repetition. So we don't care about that. Then the third position is also 10 of them. Okay, because can repeat, and over here will be 10 option. Okay, and over here we also 10 option. Okay, then how many total? Okay, how many total? So the total, okay, the total possible, the total possibility, okay, possibility will be what? Will be 9 times 10 times 10 times 10 times 10. Okay, which is give you this is 1,000, 10,000, 90,000, 90,000, 90,000 get code we can get out of this number. That's a lot, right? That's a lot. 90,000 get code. Now think about it. You have a subdivision, okay, and you want to have a get code for each family, for each resident, okay, for each house. Then you think about it, and there's no subdivision contain 90,000 houses, barely, okay. Well, if it has, in most of the time, you see that subdivision in probably have like 1,000 houses only, or maybe less. And you see that from here we can create 90,000 options already. So, permutation, the counting principle here, you see that it's gonna help us see and help us create the gate code easily for large subdivision if you want it. Okay. All right. Now let's see if we can do another one here. It's an interesting problem right here also. Example number 5. Okay. So I have some natural number like this. Okay, given 0, 1, 2, 3, 4, 5, 6. So I have 7 digits over here. And the question over here is the first question over here is how many natural number okay, how many 5 digit, okay, let me change a little bit right here. Okay, how many 5 distinct digit natural number, okay, can we create? Okay, that's the first question. Okay, I don't know, we create, there's a T over here now. I think there's a T and E. Okay, question B, how many 5 digit, again 5 distinct, okay, 5 distinct digit, okay, 5 distinct, this one, 5 distinct digit even number, even natural number, okay, can we create? This is interesting problem. Okay, And let's see how we're gonna do this. Okay. So we want a natural number, and this natural number here is 5 distinct digits. Of course, the 0 is not supposed to be in the front. Okay, so so 5 digits. So 5 digits: 1, 2, 3, 4, 5. So 0 is not allowed to be in the front. It means that we have only 6 options. Okay, we have 6 options for the first digit position. Then we have 7 for the second digit position, and the third one we have 7, 7, and 7. Okay, so we allow to have a repetition. So for example, we allow to have 1, 0, 2, 3, 4, 5, 6. This is natural number. Then we allow to have 0 repeated. 1, 0, 2, 3, 4, 6, 5. That is one example. You see that? So totally, how many? Okay, totally we will have 6 times 7 times 7 times 7 times 7, which is a pretty big number, guys. So we're gonna have 7 raised to the 4 times 6. So total we have 14,406 5 distinct digit natural number. Oh, hold on. I think there's something not right because this is distinct. So because it say distinct over here, so we're not allowed to have repetition. I'm sorry. So we're not allowed to have repetition. It means that we have 7 over here, so we're not allowed to have repetition over here. So it means that in this case, okay, the third position is not repeated. It's not the same as the second position. It means that over here we have only 6 options, 5 options, and 4 options. Okay, I'm sorry. This is distinct. Okay, so let's change a little bit. So this. Okay, so we 6, 5, and 4. Hey, let's go ahead and do the math again. So we have 6 times 7 times 6 times 5 times 4, which is 5,000. This 6. I mean, this should be 1, 2, 1, 2, 3, 4, 3, 4, 5, 6. 6, 1. I don't know. I got something wrong over here. It's because I feel that there's something not right. So we're not allowed to have 0. It should be 6 option. Okay. We have 6 option here. Then we have. Oh, okay. There's something wrong right here. So we have only 6 over here. 6 option over here already, because we're not allowed to have 0. Then on the second position, we don't want to have it repeated because it's distinct. Oh, I'm sorry. Okay, so let's yeah. So over here should be 6 too. So okay. Careful. See the very big. You have to be careful over here. So we have 6 options here, and we don't want the second position to be repeated with the first one. So it means over here we have only 6. We don't want to have this one repeat with this and this. So we're gonna have 1, 2, 3, 4, 5. Then we have 4 here because we don't want to have it repeat with this 3 over here. So we have only 4 options left, and we have 3. So we have 6 times 6 times 5 times 4 times 3. There you go. So the total will be 2,160 distinct digit natural number. Okay, 5 distinct digit natural number. Okay, so let me erase this one. All of them is distinct. All of them is distinct. Okay. Alright, now part B. How many 5 distinct digit even? So we need to know what even number. So even number is the number the last digit is even or 0. Okay, so let's see how we do this one. This concept is this problem example number 5 is more challenging than the first 4. So let's say that, okay, let's say that because the last digit is supposed to be 0 or even number. So over here must be 0. Okay, over here must be 0. So we have only one option right over here. Right, for a 5. So 0 over here because there's only one option over here. Okay, so 0 must be here. Let me use different so this is only one option because even, okay, even it means the last number, the last digit must be 0. So there's only 1 0 here. Then over here we have one option. Then over here you will have 1, 2, 3, 4, 5, 6 option right here. Okay, you have 6 option for this one. Then you have 5, then you have 4, you have 3. Okay, then totally you will have what? Then totally you will have 6 times 5 times 4 times 3 times 1, which is how many options we have? 6 times 5 times 4 times 3, 6 times 5 times 4 times 3 times 1. So go ahead and put into the calculator. Okay, so we have totally 360 options. When 0 is the last digit, which is, it means even number. However, the even number we can create by put the even number as the last digit. Okay, so it means as the 5th position over here. The 5th position over here could be even number, but not 0. So it could be 2, 3. It could be 2, 4, and 6. So we have 3 options here, right? It could be 2, 4, and 6. Okay, then we have 3 options. Then over here we're not allowed to have 0. Then we have 1, 2, 3, 4, 5, 6. We don't want to repeat over here because all of them distinct. So we're not allowed to have 0. So it means that we have 1, 2, 3, 4, 5 options only. Right? Yeah. Then for this one right here, we allow to have 0, but we're not allowed to have the same as this one. and that one. So totally we have 5 option, then we have 4, then we have 3. So totally we have 5 times 5 times 4 times 3 times 3. Okay, which is give you 900 option. Okay. Okay, so you see the problem here is more challenging, and I did it on purpose because I start from the easy one, then I go harder and harder. Of course, some problem is much harder, but I don't want to include it over here. Then totally, total we have 360 plus 900. So total we have 0, 6, 1260 even 5 distinct digit even natural number. That's what it is. Okay, good. All right, so that's the first topic in this lecture. Now the second concept I want to talk about, we call that permutation. Okay. Now before we jump into the definition of what permutation is, I want to talk about one of the operation. Maybe you never seen this operation before. Back in the day when you're in high school, you know how to add, subtract, multiply, divide, exponential, absolute, and radical. But this operation we call that factorial. Okay, I'm sure you never heard of it before. Factorial. So what is factorial? Okay, factorial of a number. Okay, factorial of the number is a positive number, because we cannot find a factorial of a negative number. Is notated as, okay, so a number n. So factorial of a positive number n is notated as a n, and with this mark right over here. Okay, I don't know what this mark called. I just suddenly forgot. Yeah, sometimes it just my brain sometimes go blank like that too. But with n and with this mark right here, this is I try to Google this. What's the stack mark called? Yeah, I just suddenly forgot. So we read this is the factorial of n factorial, and n factorial over here. Okay, is equal to n minus 1, n minus 2. Okay, and you go on all the way down to 3 times 2 times 1. Now let me give you an example. It's not hard, very easy. First of all, I want to calculate the factorial of 5 factorial. Okay, so 5 factorial actually is a product between 5, 4, 3, 2, and 1. Okay, so over here it will give you what? It will give you you multiply, give you 20 times 60, 60 times 2 is 120. So 5 factorial is 120. You can do operation with your graphing calculator. I'm sure you scientific calculator, you can use that to calculate n factorial easily. And what if I have something like this? What if I have a fraction between 2 factorial? What if I have this? What if I want to calculate pretty big number? What if I have well, let's do small number like this, 9 factorial over 6 factorial. Okay, now if you go ahead and apply this formula right here, you will see that 9 factorial actually is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1 And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Okay, I missed number 2 over here. Okay, 3 times 2 times 1. Now I go ahead and cancel them. Okay, then 9 factorial or 6 factorial is equal to 9 times 8 times 7, which is give you 504. Okay. Now what if the n value is 0? Okay, n value cannot be negative, so I'm gonna put over here. So n must be positive. Okay, but what if n is 0? Okay, so it means that we have 0 factorial. 0 factorial is equal to 1. Okay, remember that 0 factorial is equal to 1. Okay. Why we need to know this operation? Because in the formula of in the permutation formula, it's related to factorial operation. So if we don't know how to, you don't know what factorial is, you don't know how to do permutation formula. You don't know how to use it. Okay. Now, after we know factorial, then let's see. Let's talk about the definition of permutation. Okay. So definition of permutation. So if you notice in the first Roman, when we talk about counting principle, one of the example we start arrange the number. Remember, talk about the gate code. We arrange the number in the position, in the digit position. And I say the permutation and counting principle is related because permutation is actually is just also arrangement. Okay, but the way we arrange in permutation is different. We have to arrange with order. So permutation is actually is an order arrangement. Okay. Okay. I'm gonna put this the same color over here. So permutation is order. It must be in order arrangement. Okay, it's an order arrangement of item. Okay, so it all the item must be arranged in order of item. Okay, that occur when no item is used more than once. Okay, when no item is used more than once. Okay, very important right here. Okay, so remember we talked about the arrangement in of number to create a gate code. Some element over there it can be repeated. Okay, but however, if the problem is related to permutation, the arrangement is never repeated. Okay, it never repeated. That because no item in the group is used more than once. Okay. All right, now let's jump into our first example right away. And some when we do example, I will tell you in some example we can do counting principle and permutation at the same time. Okay, what if I have this? Okay, I had a problem like that. Okay. A corporation has 7 members on its board. In how many different ways you can elect a president, a vice president, and a secretary? Okay, let's see how we do this. So, oh, I forgot one thing. I forgot to give you the formula. Oh, I forgot. Let's go. Ooh, just sorry. I have to give you guys a formula before we can do anything. Okay. So I'll put example 1 here and so here. So okay, let me give you the formula to calculate the permutation. Okay, so permutation is noted as P. Okay, and if we pick N and we pick R item, okay, we pick R item from N items in order, so we can write NPR, okay, equal to N factorial over N minus R factorial. There you go. So this is the formula. Okay, the most important thing in order to use it is that we need to know which one is N, which one is R. Okay, let's jump to the first example. Let's see which one is N, which one is R over here. So there are 7 members. Okay, so it's 7 members. So over here 7 must be N because we pick a group that has 3 members, president, vice president, and secretary. And this group over here we have to create in order. Okay, because the president and the vice president and the secretary, so everything must be in order, and because it's in order, so it's this permutation. So we can use a formula over here. So in this case will be 7 and R is 3, so we can use the permutations. Will be 7 3 will be 7 factorial, and 7 minus 3 factorial, which is 7 factorial over 4 factorial, which is give you 7 6 5. Okay, which is give you okay, look like my R number is wrong. I'm sorry, it says the R number over here. Yes, because this group over here they select is their 4 position. So R is 4, guys. Okay, so let's delete this. So 4. Okay, so over here which is give you 3. Okay, then over here you have times 4. So you take all of those numbers, you multiply each other. So you have 840. So we have 840 options to create a board of director containing these position. President, vice president, secretary position, and treasurer position. Okay. Now, if we apply the counting principle, it's a very interesting thing too. Now, if I do the second method, we have 4 positions, and we apply the counting principle, you will see that it turned out to be the same. Look at it. We have the first one. We have 7 member, right? So the first one we have 7. Okay, it's not repeated, so we have 6. 5. We have 4. Okay, because it's not repeated. That's according to the definition. There's no item is used more than once. Okay, so you see that at the end you have 7 times 6 times 5 times 4 using the counting principle will give you the same thing. So you see that that's why the permutation and the counting principle related to each other. They actually the same. But this good thing over here is that for permutation we can apply the formula directly. Okay, It's up to you. When you do the problem, it's up to you. You can use a permutation formula directly, or you can use a counting principle. It doesn't matter as long as you get the final answer. It'll be okay. Now, example number 2. Okay. Okay. Example number 2. Okay, I had a problem like this. How many different programming schedules can be arranged by choosing 5 situation comedy from a collection of 9? Okay, can be arranged by choosing 5 situation comedy from a collection of 9. Okay. And now we can go ahead and apply the permutation right away. Order is important, right? Order important because we don't want to create a schedule that have repeated uh, comedy. So we have 5 comedy, we have 9 classic sitcom. Oh, look like, isn't this one permutation too? Did I pick a permutation problem? Let's pick it again. I don't know if I picked the correct one. Yeah. Yeah, I picked the correct one. Okay, so let's see how we do this. How many different programming schedules can be arranged by choosing 5 situations? By choosing 5 situation comedy from a collection 9. From, okay, not and. From a collection. So totally we have 9 classic sitcom and we pick only 5. And we don't want to have it repeated. Okay, so we can do like this. So n over here must be 9 is 4 or 5. So we can do 9 5, 9 factorial, 9 minus 5 factorial. So you're gonna end up with a 9 factorial over 4 factorial. You're gonna end up with 9 times 8 times 7 times 6 times 5. So go ahead and multiply all of them. You have 15,120. 15,120 schedule. Okay. And if you apply the counting principle, do the same. You gotta go ahead and draw 5 position. And you see in that position, in that schedule, there's no way. If you do like this, if you do counting principle, this is how you do. For example, you have a schedule like this. Okay. And in this schedule, we have 5 positions. So we have the first comedy, we have the second one, third, 4. Okay. And 5. Okay. And let's say that this is the schedule. This starts from 4 p.m. Then this is go to 6 p.m. and 8 p.m. start, and it's 10 p.m. and this is 12 p.m. We have another show. Okay. Actually, I should start a little bit early. Nobody go to the comedy at this time. So let's change the schedule a little bit. That is the schedule. This is just for fun, okay? Okay, it's just for you to understand the situation. What's wrong with this? Okay, let's do 2, 4, 6, 8, 10 p.m. And you see that there's no comedies repeated, because if it is repeated, you have 2 and 6. In this case, we don't want to repeat it. We don't want to. So the first one is the first comedy, and the second comedy, and third, and fourth, and fifth one. Okay, so that's why we have 9 options here. We have 9 options here. Then we have only 8. We have 7. And we have 6, and we have 5. You see, you multiply them up, which is give you that. Okay. Example 3. Okay. Same thing over here. In how many ways can a letter of osmosis can be arranged? Okay. Now, this example number 3 here is a little bit different, because you see over here, in the previous example, the n value over here is different. So we have 9 different characteristics. But over here, 1, 2, 3, 4, 5, 6. There's 6 elements. They ask you to rearrange this. But some element over here is repeated. So 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. If we do the counting principle, you will see that some of them is repeated. Okay, and you see that the letter over here is present twice, and the letter S over here is present 3 times. So even though I change the position of letter O or letter S between them, it gives you the same word, which is not good, right? Okay. So if you use the permutation formula, it probably give you a wrong answer, because some letter over here, some element over here is repeated, and because it's repeated, this is what you're gonna do. So 1, 2, 3, 4, 5, 6. So over here you're gonna have a 6 factorial rearrangement. Then you divide by the factorial of the letter which is repeated. So over here divide by 2 factorial. S little repeated 3 times, so divide by 3 factorial. Then it's gonna end up with different arrangement. Okay. So over here, you're gonna have 1, 6, times 5, times 4, times 3, times 2, times 1. Then you have 2 times 1, times 3, times 2, times 1. And you cancel this. Then you're gonna end up with like 120 divided by 2. So you end up with 60 options. Did I do anything wrong over here? So, and letter. Yeah, it should be good. I don't know if I calculate anything wrong. 1, 2, 3, 4, 5, 6. Okay. Letter O, 2 of them repeated. Letter S, 3 of them repeated. So 3 times 2 times 1. So we have 60. There's something not right over here, guys. feel like there's something not right. Osmosis. Because before I calculate it, it's not 60. So I try to find somewhere which is wrong over here. Sec factorial. Does this one 2 repeated? S is 3 repeated. Because identical. It should be okay, but I don't know why before I don't get this number at all. And I throw away the I remember I don't get 60. But I check it, there's nothing wrong over here. 3 factorial is 3 times 2 times 1. Because the letter S is repeated 3 times. Letter O is repeated 2 times. Yeah, there's nothing wrong. Divided by 2. Yeah, I think it should be okay. I think it should be okay. I don't know. I cannot find something not good over here. But it look like this is good. Look like this is good. Now let's jump to the next example. Okay. Oh, this one I already did it. Okay. How about this one? Answer. Okay, so we have a bicycle club, 5 different routes. Member wish to travel exactly one, but they have 6 specific days for the trip. Okay, 6 specific days for the trip. In how many ways? In how many ways can different route be assigned to the date? Okay, so you have 6 specific dates. So just imagine if you apply the Cartesian principle, you have 6 specific dates. Okay, and you don't want to repeat it. Okay, so it'll be 10, 9, 8, 7, and 5. 10, 9, 8, 7, 6, and 5. See that? Easily. 10, 9, 8, 7, 6, and 5. You multiply them up. However, if you apply the permutation formula, you're gonna do it like this. P 10, 6 will be 10 factorial over 10 minus 6 factorial. So you will do 10 factorial over 4 factorial. That's why you're gonna with 10, 9, 8, 7, 6, and 5. See that? It's gonna give you the same number, 151,200. Option. Alright. See, so for over all this, for example, you see clearly that there's a relation between permutation and its accounting principle. Okay, so I think I'm gonna stop right over here. If you have any question regarding to any example over here, please let me know. Then I'll be see you next time for the new concept of computation. I'll see you. Bye bye.